Hi, this video is about the concept of power in physics. Power is the rate of doing work. In other words, power is a measure of how quickly work can be done. Power is equal to work divided by time, and we abbreviate power with a capital P. So capital P equals capital W over lowercase t for time. Doing work quickly results in a higher power output. So remember, we are talking about the work that's defined as force times distance. Doing schoolwork more quickly does not make you more powerful. In fact, it'll just make you more mistake prone. So let's look at an example of power in physics. Let's say that I have a dumbbell that I want to lift, and I want to know, how can I do this work of lifting a dumbbell? How can I do it with more power? So my first question is, which one would have a higher power output, a slow lift or a fast lift? So I've got my scale here for distance, and I do a force on the dumbbell. I lift it slowly, doing work on it over a longer time. And then I do some more work, but this time I do it quicker. Which one has a higher power output? I think it's pretty clear that lifting the weight fast means that you are exercising more power. And that's what power is really all about. It's just how quickly you do the work. Now, what if we have different amounts of work? What if I lift one dumbbell, but then I take another dumbbell and stack it on top and lift the two dumbbells at the same speed as the one? This time it's the same amount of time. I did it at the same speed, but I lifted two dumbbells the second time, which requires twice as much force to lift two dumbbells. And then that means it requires twice as much work. And so even though it's the same time, this one takes more work, and that means there's a higher power output required to lift two dumbbells at the same rate as lifting one dumbbell. All right, what if I have different distances? What if I take one dumbbell and I lift it to 0.25 meters right here in the middle? But then I take the dumbbell again and I lift it at the same speed to 0.5 meters. As long as the speed is the same, which one has a higher power output? Well, if we just think about it briefly, lifting at 0.25 meters, we can do that pretty quickly. And so that would be a relatively low amount of time. I'm going to draw a little t here to represent the time, and this would take a little bit more time. So I'm going to draw a bigger t. However, lifting at 0.25 meters also doesn't take much work. It takes a force, but a smaller distance. And so the work required is smaller compared to the bigger work required to lift it half a meter. So while we're lifting this not as far, it takes less time. It also takes less work, because work is force times distance. And less distance means less work. This one, more time, but also more work. So the ratio of work to time is actually the same. So these two have the same power output. Even though they're different distances, since they're going at the same rate, the same speed, it's the same power output, because power is only about how quickly you can do the work. Let's look at one more example like this, just to make it a little bit more clear, hopefully. Let's say we got two brothers going sledding. Little brother Joe climbs the snowy hill in 30 seconds up here, but big brother Bo takes 60 seconds. Now, if you notice, I do have in parentheses here their masses. Joe is 25 kilograms, Bo is 50 kilograms. And so what's noteworthy there is that Joe is half the mass of Bo. So Bo is twice as heavy, but Bo also took twice as long to climb the hill. So if you look at the power equation for each of them, let's start with Joe's power. Joe's power is going to be Joe's work divided by Joe's time. But Bo's power is going to be Bo's work divided by Bo's time. But if you remember, Bo's work, because he's twice as heavy, is going to be 2 times Joe's work. It's going to take him twice as much force to lift him up that hill. So twice as much work, but at the same time, Bo's time is twice as much as Joe's time too. So even though he is heavier, it's going to take more work to lift him up to the top of the hill. He doesn't do it as quickly, so it takes twice as long to do it. And if you know anything about algebra and fractions, if we're multiplying 2 times the numerator and 2 times the denominator, we can cancel these out. They basically have no effect, and we can get rid of the times 2 here. Bo's power is simply Joe's work over Joe's time. And if you look at Joe's power, that's Joe's work over Joe's time. They have the same power output. So even though Joe was able to climb the hill really quickly, he's lighter. He doesn't take as much force to lift himself up to the top of the hill, and so not as much work is done. And they end up having the same power output. So how do we measure power in physics? We've done a lot of just thinking about power. But what is the unit of measurement for power? I'll say it again. What is the unit of measurement for power? Watts is the unit of measurement for power. So power is typically measured in watts, which is a joule per second, because work is joules and time we measure in seconds. And so work divided by time, joules per second, and we have a new unit for that called watts. And watts is abbreviated with a capital W, which is a little confusing because work is also capital W, but when we talk about units of measurement, it's a capital W for watts. Just to give you an idea of how much 1 watt of power is, a typical light bulb has a power output of 60 joules per second, or 60 watts. At 50% brightness, a Chromebook, I think, typically does 10 to 20 joules of work per second, or about 10 to 20 watts. This, of course, varies based on if you're running a certain application. You know, phones can do more power output if they have a high brightness and they're playing a video and doing all kinds of other things. So it depends on how much work you're putting through a computer. Walking at a slow speed, an average human has a power output of about 100 watts, to give you an idea. There is another unit for power, too, that you've probably heard of before, and that's a horsepower. A horsepower is 745.7 watts about. And, you know, it's derived from actually James Watt was trying to describe how much power a steam engine does, and he related it to the power of a horse. That's kind of the history behind it. And so horsepower is not a standard scientific unit for us in this class, so we won't be using it a lot. But that is how it's related to watts, 745.7. So I think that's all I've got for you in this video. Remember, habit is the battleground of character.